An elevator of weight W rides in a vertical shaft with negligible friction. The tension in the cable is held at a constant force equals 1.18 W. If the elevator starts from rest in position A, calculate the maximum displacement x max. Okay, so let's see. So we have an elevator starts here, and there's tension in here, but you can't hold it vertical like this because the tension doesn't work out. And so it's going to fall until enough of the component of the tension going this direction is equal to the weight of the elevator, therefore holding it in equilibrium. This would be a terrifying elevator. So you basically get in and you basically just drop until the forces equal out. So the force here is a little bit more than the weight here. So I'm going to rewrite this real quick. Instead of saying 1.8 weight, I'm going to call this mass times gravity, because that makes it a little bit more obvious that it's the force. And then if we look at the weight of the elevator, what we have here is we have a force gravity downward, which is going to be mass times gravity, which has been labeled as weight. And as the elevator goes down, this angle changes so that eventually the vertical component of this tension vector here, I'm going to call it right there, will equal the weight of the elevator. So I'm going to draw a triangle. Like all good physics problems, starts with a triangle. So the tension is going to be 1.18 here. We're going to have some sort of theta right there. And we are going to know that this is going to be mass times gravity. So if we look at this, we do sine of theta times 1.18. Mass times gravity, put a little mass times gravity there, and that will equal mass times gravity. Oop, get the canceling. Nope, not enough contrast. There we go. And when we start looking at this, then we solve for theta, we'd have theta equals sine inverse, I'll say arc sine of 1.18. Solving for theta, using a calculator, make sure we're in on mode, we're in degrees, it's good. I like degrees, radians work too. Second, arc sine of, 1 over 1.18. So we move it over, 1 over 1.18. Good catch. 1 over 1.18. There we go. And we get like 57.94 degrees. 57.94 degrees. So basically this is saying that the elevator drops until this theta here is 57.94 degrees. Therefore, at that point, the vertical component's enough to hold it up. It'd probably actually bounce around and oscillate. It'd be a terrible ride for the passengers, but that's not really, I think, what they're going for here. So then it asks, what's this displacement x max? That also bothers me. It should be y max because it's vertical. It's okay. I'll get over it. So what they're asking for then is, if we look at a similar triangle, like so, and we're told that this is 2 meters right there, so we have 2 meters, and we're given this theta right here of 57.94, kind of, sort of. We want to find that angle right there. So TOA, our little mnemonic to remember the trigonometric identities. And so we're going to want an opposite over here, an adjacent. So we'll be using tangent of theta equals opposite over adjacent. Solving for opposite, because that's going to be our x max, which is really a y value, equals adjacent times tangent of theta, which will be 2 times tangent of 57 degrees. And that will give us, tangent, second answer, close parentheses, times 2. We get 3.19. Yeah, I'm going to get that. So y max, x max, equals, I said 3, right? Did I say 3? I said 3. 3.19 meters. So if we have a constant force of 1.18 weight, then this would be 3.19. There we go. 3.19 meters, assuming that this distance right here is 2 meters. And yeah, this sounds like a terrible... This is probably why I imagine the, well, that and just for engineering purposes, fitting everything within the shaft. I assume that for elevators, that's why it hangs straight down as opposed to off at a funny angle like that. Because that would be terrifying. You'd drop like probably 6 feet before it really catches. That'd be terrifying. Terrifying. Okay. Hope that helped with the concept. I will see you next time.